Welcome back to the lecture series on analysis in state space. So far, we have completed 3 lectures on solution of state equation, stability, controllability, and observability. In this lecture, we will see how we can test the systems for stability, controllability, and observability. This is going to be the last lecture in this series on state space modeling and analysis. Before going into the topics of this lecture, we will have a quick review of what we learned in the previous lecture. If the state space model is represented by this state equation and output equation, then I can do a stability analysis on the system by locating the eigenvalues of the state matrix A on the complex plane. For the system to be stable, the eigenvalues have to lie on the left of the S plane. If any of the poles lie on the right of the S plane, then the system is unstable. And if any of the pole is lying on the imaginary axis, then the system is marginally stable. And also we studied about controllability. If I can design a controller, feedback controller, to control the states of the system, then my system is a controllable system, or in a formal way, I can define the controllability as if every state variable x of t in the system can be driven from one state to another state by an input u of t in a finite time interval, then I will call that system as a completely state controllable system, or simply I can call it as a controllable system. Please understand. So how do I know that my input is having the control over the state variables? The control input should be able to drive the state variable from one state to another state. Then only I can say that that input is having some control over the state variable. So that is why I defined if every state variable of the system can be driven from one state to another state by an input in a finite time, it has to happen in a finite time, then I call the system as a controllable system. Then we saw about the observability also. If I have an output, with the knowledge of the output, input, and the system matrices A, B, C, and D, if I can determine all the states in the system in a finite interval, then the system, I will call it as a completely state observable system, or simply I can call it as a observable system. Okay, so the formal definition is if every state variable x of t of the system can be determined from the knowledge of the output y of t, input u of t, and matrices A, B, C, and D in a finite time interval, then the system is to be completely system is said to be completely state observable or simply observable. Okay, so this is what we learned in the last class. The concepts we brought in some examples also to understand this concept of uh, controller, observer, controllability, and observability. Okay, so we took a case of a sensorless BLDC model also to understand how observer how an observer can help me in the design of a state feedback controller. Okay, so with this background, we are moving on to the tests, to understand whether a system will be a controllable system or an observable system. So those tests are the focus of this lecture. So let us assume that this is going to be the state space model, and we have already defined this controllability. So I will repeat it again. If every state variable x of t of the system can be driven from one state to another state by an input u of t in a finite time interval, the system is said to be completely state controllable or simply controllable. Now, there are two tests, there are many tests, and out of them, I'm going to give two tests for controllability and two tests for observability. First test is valid only for SISO system. So if I have an SISO system, that is single input, simple output system, which is described by the state equation of 1, if I want to call that as a completely controllable, then the condition is that the matrices A and B should be in CCF, or they should be transformable into CCF by a similarity transformation. Okay, either the matrices A and B should be in CCF, controllable canonical form, which we have already studied. What is that form? Or if those matrices are in some other form, then I, through some similarity transformation, I should be able to transform those matrices A and B to controllable canonical form. If I could do that, then that SISO system, I can call it as a controllable system. Okay, so this is the first test. And the second test is, for a system described by the state equation to be completely controllable, it is necessary and sufficient that the following controllability matrix S has a rank of n. Okay, so that is what is the second test. This is a very, very important test, and this is the test what we will be using in our further problem solving. So, what is the condition? There is a matrix X. We are all familiar with this matrix S because this is a matrix which is useful in transforming any system from its original state space model to controllable canonical form, CCF. Okay, so this matrix we called as the controllability matrix, and I told you that this matrix is called controllability matrix because this is going to be useful in assessing the or in testing the controllability of the system. So I hope you will appreciate why we called this matrix as a controllability matrix, because this is useful now in assessing the controllability of a system. So what is the condition? This should have a rank of n, where n is the number of states in the system or the order of the system. What is going to be the size of this controllability matrix X? S. If, let me say, I have got a B matrix of 3 cross 2. B matrix is 3 cross 2, let us say. So this will have 2 columns and 3 rows, right? 3 rows and 2 columns, this B matrix. So please assume that I've taken a B matrix of 3 cross 2. So B matrix will have 3 rows and 2 columns. And the A matrix will be of the size 3 cross 3. And if I multiply this 3 cross 3 matrix with a 3 cross 2 matrix, I will again get a 3 cross 2 matrix. So therefore, the product AB also will be a 3 cross 2. Okay, right. Please note, when I say that B is a 3 cross 2 matrix, it means that 3 states and 2 inputs. Okay, so that is what. And A square is going to be again 3 cross 3, and if I multiply it by a 3 cross 2 matrix, then this product is also going to be 3 cross 2 matrix. Therefore, I got 3 cross 2, 3 cross 2, 3 cross 2. So I will get all 3 cross 2 matrices. So S matrices is going to be a super matrix containing many sub matrices of the order 3 cross 2. The number of rows is always going to be 3, or it is going to be the number of states n, and the number of columns is going to be n into r, otherwise 3 into 2. Okay, 3 into 2. So 6, number of columns will be 6. Otherwise, I can say the 3 into 2 as 3 is the number of states and 2 is the number of inputs. Therefore, I can say the number of columns is going to be nr, n into r. So that is why this matrix is going to be a rectangular matrix, and this order of the matrix will be n cross nr. Okay. So if it is an SISO system, this B matrix will be a column matrix, and it will have only one column, and therefore this number of columns also will be equal to n. Anyhow, whether it is a n cross nr or n cross n, the maximum rank that this system, this matrix can have is equal to n. So if this matrix is having a rank of n, we call this matrix as a full rank matrix. Okay. For example, if it is a 3 cross 6 matrix, then the maximum rank is going to be 3. And if the rank is 3, then I call this matrix as a full rank matrix. Okay. So the condition for the system to be completely controllable is that this S matrix should have a rank of n. That is, it should be a full rank matrix. S should be a full rank matrix. So this is the test. This is the condition for the system to be controllable. Okay, right. And we have not derived this, please note, and only the results are given. And also one more thing to be noted here is, in this entire definition of controllability, the matrices involved are A and B. Whether it is the first test or the second test, the matrices involved are only A and B. So if I know the matrices A and B, I can say whether the system is going to be controllable or not. Okay, so since the matrices A and B are involved, sometimes we say the pair, instead of saying that the system is controllable, we say that pair A and B, A comma B, the matrix A comma B is controllable. So which implies that the matrix S is a rank n. Okay, right. So this is the test for, this is the test for the system to be controllable. Okay, right. And as I said, we do not have any proof. If at all you are interested in looking at the proof, a generalized analytical proof, you can refer the Modern Control Engineering by Ogata, and you can find this proof in page number 676 to 676 and 677. Okay, right. So anyhow, so for an undergrad, so this course is actually for the students of an undergraduate course. For those students, for them, this is out of the scope, I think. So I have not included them in this lecture, the proof. So only the results have been taken. Okay. Now let us try to understand something about the observability test. Again, the definition we have already defined. So I should be able to reconstruct, or I should be able to determine all the states with the help of y of t, u of t, and matrices A, B, and C, D. So the test here is it's a kind of dual. Okay, very similar to the test what we did for controllability. So the test is the matrix, sorry, for an SISO system, the state space model as given in equations 1 and 2 is completely observable if the matrices A and C, now here comes the state matrix and the output matrix. Okay, so if matrices A and C are in OCF, or if I can transform them to OCF by any kind of similarity transformation. Okay, so the second test is about the observability matrix, as we had the controllability matrix in controllability. So this anyhow we are all again familiar with this matrix because we use the same matrix in the similarity transformation to transform it to observable canonical form. So if you look at this size of this matrix, this is going to be a C vector which will have, let us say, equal to number of outputs into number of states. Okay, number of rows will be equal to number of outputs, and the number columns will be equal to number of states. So again, CA will give me the same matrix of same size, and therefore the number of columns is always going to be equal to the number of states n. So whereas the number of rows will be increasing with respect to number of inputs and states. For example, so if this is this C matrix will be a number of rows in this C matrix will be equal to number of rows, and this is again number of rows, and it will be repeated n times. If I say the number of outputs is going to be m, the number of rows is going to be m into n, and the number of columns is going to be n, and the maximum, so therefore the size of this matrix is going to be m n cross n, and the maximum rank of this matrix is also going to be n. And if this observability matrix is having a rank of n, then I say that the corresponding system is observable. Okay, so please note that there is a small mistake. This is not an SISO system. This definition is valid for any system, even for MIMO system. Okay, right. So again, so here we use only the matrices A and C. So we say the pair A comma C is observable, which implies that V is of rank n. And again, if you're interested in the proof, you can refer this book, and it is given in pages 683 and 684. Okay, so now we'll take up a few examples to understand how we can analyze the system for stability, controllability, and observability. So let us take the first example. These are the matrices of the state space model. A, B, C, and D are given. Let us have some observation from this matrices. So just by looking at the matrices, what immediately I understand is this is a third order system with only one input, because the number of columns in the B matrix is 1. And since this state matrix, A matrix, is having a size of 3 cross 3, I understand that it is having a 3 state variables, and size of C is 1 cross 3, and therefore it is having only one output. Okay, and the output, if you see, y of t is equal to x1 of t and x2 of t, because we have got 1 1 in x for x1 and x2. Okay, so this means that the state variables, as I have already told you, we call some variables as the outputs if they are measurable. So from this expression, what we understand is x1 and x2 are either measurable individually or they are measured together. Okay, so x1 plus s2 is obtained together, or maybe it is measured individually and added then later. Okay, so that is what is the understanding we get from this. And if I want to do a state feedback control in this for this system, then see, the measured states are only x1 and x2. So for a state feedback controller, I need all the states x1, x2, and x3. So since x3 is not measured, definitely I need an observer to implement the state feedback. Okay, if at all I want to implement a state feedback control, then I need all the state variables, but only two state variables are measured here. And since x3 of t is not measured, I need a state observer so that I can implement the state feedback controller. Okay, so let us see the analysis one by one. First, let us talk about the stability analysis. Okay, so how do we find out the stability analysis? We take the eigenvalues of the state matrix. So this is how we take the eigenvalues lambda I minus a determinant. You take the determinant, you get a polynomial, equate it to 0, find out the roots of the polynomial, you get the lambda values or the eigenvalues. Now you have to see whether these eigenvalues are going to lie on the left side of the complex plane or on the right side of the complex plane. So if you look at so if you look at carefully, this eigenvalues, the first eigenvalue is a set of pair of complex conjugates, and they have a negative real part, and therefore obviously they are going to lie on the left side of the complex plane. If I assume this as the complex plane with the real axis and imaginary axis, they are going to lie on the left side of the complex plane. But there is one more eigenvalue 3.5251, and this is a real number, and this is positive, and this is going to lie at the right side. Even if one of the pole or the eigenvalue is on the right side of the complex plane, then the system is not observable, sorry, not stable. So altogether the system is unstable. Okay, so this is an unstable system. So that is what is the conclusion. So now please note, since this is an unstable system, definitely we need a controller so that the system, we make it as a stable system. So before implementing a controller, what I have to do is a controllability test, because whether I can find a controller, whether I can really design a controller. Okay, so that is the question. So that is the answer I will be getting from this controllability test. So if the controllability test fails, then it means that I cannot design a controller for this. So before going into design of any controller, this test has to be done. So let us do the controllability test. So we know we have to find out the S matrix. So as usual, we found the S matrix, and now we have to find out the rank of this matrix. So how we can find out the rank of this matrices? So easy way to check whether this is a full rank matrix or not. The one thing is, you can find out if it is a square matrix. For example, if it is an SISO system, you will get a square matrix like this, and you have to find out the determinant of the matrix. You can find out using the calculator, any scientific calculator, find out the determinant of this matrix. If you get a non-zero value for the determinant, then definitely you can find out the uh, uh, inverse. That means it is a full rank matrix. The rank is going to be 3. If the determinant happens to be 0, then it is going to be a rank deficient matrix. Otherwise, rank is going to be less than 3, less than the order of the system, order of the matrix. Okay. So other way is to find out the rank of a matrix is you have to reduce this matrix to a row echelon form. Row echelon form is an upper triangular matrix with all ones in the main diagonal. Okay, so using elementary transformations. Okay, that you can refer any mathematics book, and you can reduce it to this reduced row echelon form. And now the number of non-zero rows gives you the rank of the matrix. So if we find in that way, anyhow, this rank of this matrix is going to be 3, which implies that the system is controllable. Therefore, even though the system is unstable, definitely I can go ahead with the design of a controller, because I can design this is a controllable system and I can design it. And let us do the observability test. In the same way, we found the V matrix, and we found that V matrix rank is also 3, and therefore this is 3 is equal to the number of states, right, in both cases, and therefore this is an observable system also. So I can, even though this is an unstable system, I can design a state feedback controller using an observer, and I can make the system a stable one. Okay, so that is the observation. And let us take another example. And these are the matrices. So let the matrices of the state space model be this. This is also a third order system with one input, three state variables, and one output. The output is given by y of t is equal to x2 of t. Okay, so this means that x2 alone is measurable. Okay, so it has got C has got only 1 in x2 place. Okay, so therefore it is y of t is equal to x2 of t. This means that x2 alone is measurable. Okay, but for feedback anyhow we need all the state variables, and therefore it is necessary to implement an observer. Okay, so that I can have a state feedback control. Okay, let us do the analysis. So let us do the stability analysis first. Stability analysis says that if I find when I found this eigenvalues, these are the eigenvalues I get. So these eigenvalues will be uh, 2 comma 2 comma 1. So all are positive. So all are going to lie on the right side of the complex plane, and therefore the system is going to be an unstable system. Okay, right. So anyhow, I have to design a controller so that I can make the system as a stable one. So let me do the controllability test. So when I do this controllability test, when I form this matrix S, what I get is this. Okay, look at this, all zeros. Okay, so immediately, and these two rows are linearly independent, and you may follow whatever the principle I said. For example, if you expand this matrix to find out the determinant using this row, this determinant of this matrix is going to be 0, and therefore this is a ranked efficient matrix. This will not have a rank of 3. This will always have a rank something lesser than 3. And if you want to know the exact rank of this matrix, you need to go for reduced row echelon form, and you have to find, and it is found that the rank of this matrix is 2. Therefore this is an uncontrollable system. There is no need to spend time in designing a controller for this system. That is what it says. So now let us do the observability test. So observability test also fails. Two columns become 0. Therefore, the only non-zero column is this one, and therefore the rank is going to be 1. Rank of is 1. This also implies that the system is unobservable. So the system is unstable, uncontrollable, and unobservable system. Now you will have a question, why is this so? Okay, so we'll just do a little examination. So let us take the first system first. Okay, the example 1, these are the systems. If I write this differential equations here like this, what I find is that this x1 and x3 are connected to u, the control input u, because here 1 comes in the B matrix. Therefore U appears in x1 dot and x3 dot, and the x1 and x3 are directly connected to U, and therefore I can say that x1 and x1 and x3 depend on U. Otherwise U can control x1 and x3. At the same time, if you look at this equation, okay, so x2 depends on x3 and x2. Okay, so therefore if I can exercise some control on x1 and x2, that will in turn control x2 also. Therefore with the help of this u, I can control all the state variables. That is why the first system was controllable. And now let us look at this output equation, x1 and x2. So 1 1, C matrix is 1 1, so therefore x1 and x2. That means x1 and x2 influence the output y. That's what it means. And at the same time, x1 and x2 x1 and x2 are influenced by x3 also, because in both x3 we have. So therefore, x3 also will have a indirect influence on y, which means that y is connected to both x1, x2 and x3. So therefore, I can definitely determine, the x1, x2, x3 from this output. So that is why this was a controllable and observable system. But let us take the second example. Okay. So if you take the second example, see, control input is there in only x3. So x3, you will have a control input, control in on x3, and this x3 appears in x1, and therefore x3 will, through x3 you will have a control on x1. But at the same time, neither x1 nor x3 appears in x2 dot equation. Therefore, x2 is isolated, and you will not have any control on the variable x2, okay, because x2 depends on x2 alone. So the controllability is a question, because you will not have any hold or any control on the variable x. So therefore, the system is uncontrollable. Okay. And similarly, if you take this output equation, output depends only on x2. Okay. So we have already seen that x2 is decoupled from x1 and x3. So therefore, this x1 and x3 will not have any influence on, direct or indirect influence on y, and therefore, if even if I have y, I will not have any details of x1 and x3, and therefore the system will not be observable. It is an unobservable system. So this is another way of finding whether the system is controllable or observable, but this in not on manual inspection. Okay, so that is why we go for a matrix determination that is easy to implement in programs and all. So just form the matrix and find out the rank of the matrix. You can say whether the system is controllable or observable. Okay. Now, let me take another example. So here I have taken two examples, example 3 and example 4. If you look at this matrices, these set of matrices, you can easily observe that this is in controllable canonical form. Okay. And obviously, you can say that since this is in controllable canonical form, you will say that this is a controllable system. And I write the same system in observable canonical form, OCF. Okay, same system. This A is transpose of this, and this C is transpose of this B, and this B is transpose of this C. So it is just the same system represented in CCF and OCF. So now the question you can easily say that since this is in OCF, I'm able to write it in OCF. So this should be an observable system. Okay, this should be an observable. This is actually true. This is what we call it as the principle of duality. Principle of duality. So it gives a relationship between the controllability and observability, the principle of duality. It says that if the pair A comma B is controllable, it implies that B transpose is actually C, and B A transpose is the C in A transpose is the A in OCF, B transpose is the C matrix in OCF. So that also should be observable. So controllable system should be an observable system, and an observable system should be a controllable system. This is the principle of duality. But here we have to take a caution. So, but when I do this, the results are slightly different. This is normally true. Okay, but for this specific case, I find that that doesn't work out. For example, for when I write it in CCF, this is controllable, but when I find this V matrix, if you find this determinant, it will become 0, and this is rank deficient matrix, and the rank will be 1. That means the system is unobservable. This is a bit contradicting, right? And similarly, I can say that in this form, when I wrote it in OCF, controllability test failed, but observability test passed. You can verify these results. Okay. What is the reason? The reason I can find, if I write this, if I find the transfer function for the system. If I find the transfer function, what I find is there is a pole zero cancellation. Pole zero calculation. One pole and one zero gets cancelled. These two factors gets cancelled, and what will remain is only s plus 0.5. So this helps me in finding out a conclusion that to be a completely state controllable or observable system, the transfer function must not have any pole zero cancellation. So, this principle of duality is valid only if there is no pole zero cancellation in the transfer function. This is a point to note. Otherwise, the principle of duality holds. Okay. So, in this lecture, what we have understood is that we understood about the controllability and observability, and we found understood how I can test the systems for the controllability and observability, of course using the rank of the system, rank of this controllability matrix and the observability matrix, uh, and it should have the controllability and observability matrices should have the full rank. That is the test for the controllability and observability. And also we understood about the principle of duality, but the principle of duality has to be exercised with caution. That is, there should not be any pole zero cancellation in the transfer function. Okay, so this is how we complete this lecture. So far, we have completed various topics on modeling and analysis in state space in a series of 12 lectures. All these lectures were given as a part of online course delivery from home to my students during COVID-19 lockdown period. Thank you for watching all these lectures, and you may share with your friends if you think it is useful to you, or you can subscribe to that channel as more lectures will be added on other relevant related topics. Thank you. Thank you for watching.